Long before we had screens in our pockets or even electricity in our homes, humanity was already obsessed with the idea of outsourcing its thinking. It started with something simple, a tally mark on a bone, a stone moved across the ground to count something that mattered. That was the quiet beginning of computation. Over centuries, those simple marks turned into tools, the abacus, mechanical calculators, intricate astronomical devices built from bronze gears. In those machines, logic wasn't abstract, it was physically carved into the hardware. If you wanted a different result, you had to rebuild the machine itself. Then something changed. We realized that the thinking didn't have to live inside the metal. During the industrial age, engineers started imagining machines that could follow instructions, a loom that could weave different patterns just by swapping punched cards. That idea, separating instructions from machinery, was the first real glimpse of software. But gears and steam had limits. Friction slowed everything down. When we harnessed electricity, and eventually the electron, everything accelerated. Vacuum tubes replaced gears. Transistors replaced tubes. We shifted from physical motion to pure logic, from mechanics to mathematics. Mainframes filled entire rooms. Personal computers shrank onto desks. Then the internet stitched the world together. And now we live in the age of artificial intelligence, where machines don't just execute instructions, but learn from data. So that raises the real question, what is computer science actually? Alright, let's break it down. In this video, we're going to explain computer science in 8 minutes. When people hear computer science, they usually imagine someone typing lines of mysterious code in a dark room. But that's like saying architecture is just hammering nails. Coding is part of it, but the field itself is much bigger. At its core, computer science is the study of information, how we represent it, how we store it, how we move it, and how we transform it into solutions. To understand that bridge, we have to look at two worlds, hardware and software. Hardware is the physical foundation, silicon chips, copper wiring, microscopic circuits switching between high and low voltage, what we call ones and zeros. At the lowest level, everything reduces to electrical states. But humans don't think in voltages, we think in ideas. Software is the translation layer. At the bottom, raw electrical signals. Above that, machine instructions. Above that, operating systems managing memory, storage, input, and output. And on top of that, the applications we interact with every day. Computer science is what makes those layers possible. It allows us to speak to machines in a language we understand, while the machine processes everything in binary logic underneath. The pulse of the machine. To really appreciate that, you have to look at the CPU level abstraction. At any given moment, your processor is performing a relentless fetch, decode, execute cycle. It's grabbing an instruction from memory, figuring out what it means, and then firing off electrical signals to make it happen. But there's a catch. The CPU is incredibly fast, while memory, the RAM, is relatively slow. To bridge that gap, computer scientists designed a memory hierarchy. We use lightning-fast caches right on the chip to store the data you're about to need. Effective memory management is what keeps your computer from feeling sluggish. It's the art of making sure the right data is in the right place at the exactly right nanosecond. And that brings us to code. Coding isn't magic, it's precision. It's writing instructions so detailed that a machine can't misunderstand them. If you tell a person to make a sandwich, they fill in the gaps automatically. A computer won't. It needs exact steps, every movement defined, every condition specified. That's why programming languages exist. Some stay close to the machine, giving you direct control over memory and performance. Others are designed to feel almost like English, helping you build complex systems without worrying about electrical signals. Behind every program is an algorithm, a structured step-by-step method for solving a problem. Algorithms decide the fastest route on a map. They determine what shows up on your social media feed. They compress your photos, encrypt your messages, and recommend your next video. It's about making it efficient. The science of scale. This is where we talk about algorithm efficiency. In the industry, we use something called Big O notation to describe how an algorithm's performance changes as the data grows. Think about it. An algorithm that works for 10 items might take hours for 10 million. For example, a simple linear search, checking every item one by one, is O of n. It's fine for a grocery list. But for a global search engine indexing billions of pages, that would be a disaster. We need O of log n or better. Efficiency isn't just a nice to have. It's the difference between a feature that feels instantaneous and a system that crashes under its own weight. It's why companies spend billions optimizing a single sorting process. At that scale, every saved millisecond translates to massive savings in energy and better user experience. Some problems can be solved almost instantly. Others grow exponentially harder as the input increases. In computer science, we study how algorithms scale. We analyze time, memory, and computational limits. We ask, is this problem practical? Is it solvable? Or does it become impossible at scale? Understanding those boundaries is what separates engineering from science. Then there's data. Raw information is chaotic. If you dump a million names into memory randomly, finding one specific entry becomes inefficient fast. So computer scientists design data structures, organize systems for storing and retrieving information, arrays, trees, graphs, databases, the digital scaffolding. Think about the apps you use daily. When you press undo in a photo editor, you're interacting with a stack data structure, where the last action performed is the first one removed. When you navigate a social media platform, you're moving through a graph, where every person is a node and every friendship is an edge. Even a simple search relies on a hash map, which allows the system to jump directly to the information you need without searching through everything else. Data structures are the skeletons of our digital world. They give software its shape and its speed. The structure determines the speed. The organization determines the power, handling the global load. But what happens when one computer isn't enough? That's where large-scale systems come in. When millions of people try to watch the same viral video at once, a single server would melt. Computer science teaches us how to distribute that workload across thousands of machines in data centers around the world. We use load balancers to act like traffic cops, directing requests to the servers that have the most breathing room. We use parallel computing to break one massive problem into 1,000 tiny pieces that can be solved simultaneously. It's the ultimate act of coordination, ensuring that even if a dozen servers fail in a warehouse in Ireland, your video keeps playing in Tokyo without a stutter. This ability to handle computation at scale is what transformed the internet from a collection of documents into a living, breathing global brain. As the field matured, it branched into specialized areas. Networking explores how machines communicate across the globe, how packets travel from one continent to another in milliseconds. Cybersecurity focuses on protecting those systems, building defenses against attacks in an ongoing digital arms race. And then there's artificial intelligence. For most of computing history, we told machines exactly what to do. Machine learning flipped that model. Instead of writing explicit rules, we provide data and objectives. The system adjusts internal parameters, sometimes millions or even billions of them, to minimize error and recognize patterns. Underneath the surface, it's math, optimization, statistics, linear algebra. But the outcome feels almost human. Cars that learn to navigate roads, systems that detect diseases in medical scans, models that generate language. Ultimately, computer science is about amplification. It allows human ideas, abstract thoughts, to take physical form through logic and electricity. It extends our memory. It extends our reach. It extends our problem-solving ability beyond biological limits. We built tools to help us count, then tools to help us calculate, then tools to help us think, and now we're building tools that help us learn. Looking back at those first tally marks, it's clear how far we've come, but the deeper you study computation, the more you realize something interesting. We're still at the beginning. The hardware will get smaller, the models will get smarter, the systems will get faster. But the real frontier isn't the machine, it's what we decide to build with it. And that's computer science.